Hello students, welcome to Unit 9, Lesson 1. This is a video lesson for the Intro to Polygons lesson in the Polygons unit. This is the first lesson in a new unit dealing with polygons, which are two-dimensional shapes. We're going to talk about their tendencies, but first take a look at this learning target. According to the learning target, we're going to be deriving formulas for interior and exterior angles of regular polygons and applying them to specific shapes. All right, moving on to the do now. In the do now, it asks you to do some light work, some algebra work. Pause the video and try these out and then see if you got them right. All right, in this first expression, all you have to do is substitute n equals 8 into the expression, and you simplified. Obviously, you're doing the parentheses first because PEMDAS says parentheses first, then exponents multiplying, dividing, and adding and subtracting. Same thing here, we're doing the parentheses first. 8 minus 3 gives you 5, and then we're multiplying because whatever's in the parentheses go first. That is a foreshadowing for today's lesson. Next, we move over here to an algebra problem. All we did was take all of the terms with a's, combine them together. We're combining like terms, and then combining together all the numerical terms. That gives you 0, and as you know, 25a plus 0 is just going to give you 25a. We're dividing both sides by 25 to give you a is equal to 4. Very simple warm-up to get you warmed up for the task at hand. The task at hand is dealing with polygons. Polygons are two-dimensional shapes that are bounded by straight sides, and those straight sides meet each other at their endpoints. There are a lot of different types of polygons, but you know about a lot of them already. Equilateral triangles, isosceles triangles, and scalene triangles for 3, because we've dealt with them in previous units. You also know that there are right triangles having right angles. The reason that this box is sort of straddling the two sections between isosceles and scalene is because it's possible for a right triangle to be an isosceles triangle as well. You can see that these two legs appear to be the same measure, and then with a scalene triangle you can see that these two legs appear to be different measures, and obviously, as you know, the hypotenuse is going to be different. With quadrilaterals, we're going to get really into these different types of quadrilaterals, but keep these in your mind. Parallelograms are a special kind of quadrilateral where the two opposite sides are parallel, hence parallelograms. Rhombuses are a type of parallelogram that have all 4 sides that are equal or congruent. Rectangles are a special kind of parallelogram that have all 4 angles that are congruent, they're right angles. And then a square, you can see it's straddling all of these boxes. A square is a type of rectangle, it's a type of rhombus, and it's a type of parallelogram. There is one more type of quadrilateral that you need to know about. It's a trapezoid, also known as a trapezium if you're learning about this in the UK. It is a type of quadrilateral with parallel sides, one pair of parallel sides, but the other pair is not parallel. Pentagons, hexagons, septagons, they all have the sides that are listed here, but we really go into depth into quadrilaterals and triangles in this unit for polygons. Let's move on to the think, pair, share. Obviously, you're going to have a difficult time pairing, but for each figure below, try to figure out or try to determine whether it's a polygon and explain your reasoning. I haven't given you a formal definition of polygons yet written down. That's on purpose. I really want you to think about this before we launch into it. So pause the video and try to figure out whether these are polygons. All right, here are the correct answers. You can tell that this is a polygon and so is this. They're both straight-sided shapes with the sides that meet at the endpoints, and they have an interior and an exterior, interior and exterior. This one's not a polygon because it's got 2 different interiors, doesn't count. It really is more like 2 polygons that share a vertex. This one is not a polygon either. It is a curved shape, so we don't call that a polygon. A little bit of knowledge for later when we talk about circles, which we will in different units. The circles are not a type of polygon, according to most mathematicians. Anyway, this is not a polygon either because the sides do not meet at endpoints. All right. We're going to move on to the notes section. Here's our formal definition. It's a plane figure, a two-dimensional shape with at least 3 straight sides that meet at their endpoints. You know a lot about the 3-sided ones. Those are triangles. I'm going to give you a lot more during this lesson. Regular polygon. This word regular means that it is equilateral and equiangular. All the sides are congruent. That's what equilateral means. And equiangular, all angles are congruent. You can tell that the first shape that we're going to be talking about is an equilateral triangle. Its sum of interior angles you already know is 180 degrees, and each interior angle is 60 degrees, which makes sense because if you take 180 and you divide it by 3, there's 3 angles in this bad boy. That would give you 60. You also are probably familiar with a square. A square has 4 right angles, making it 360 degrees in total, and each interior angle is 90 degrees because that's what you know about right angles. I'm going to introduce the other regular polygons to you one by one. A regular pentagon has 5 sides, like that building in Washington, D.C. You can see that the sum of the interior angles is 540 degrees. You can also see that each interior angle is 108 degrees. Now, what I want you to do, as you're looking at these sums of interior angles, I want you to try to determine what the pattern is, because I'm going to be asking you that in a moment. Similarly, a regular hexagon is going to have 6 equal sides, 6 congruent sides, and 6 congruent angles. 720 degrees is the sum of the interior angles of the hexagon, and also each interior angle, each one of these individual angles is 120, which makes sense because 720 divided by 6 is 120. An octagon, an 8-sided shape like a stop sign, should be familiar to you as well. 1080 degrees in all of these angles, and one individual angle is going to have 135. I leave it to you to determine what 135 times 8 is. Here's a hint. It's 1080. Regular decagon is the last one. A decagon has 1440 degrees in all of these angles inside of it, and it's got 144 degrees in one of them. 1440 divided by 10 should give you 144. All right, the question that I want to ask you is, do you notice a relationship between the number of sides and the sum of the interior degrees? Remember, the number of sides is over here, that's 10 for the decagon, and the sum of the interior degrees, that's this column here, 1440 for the decagon. I'll scroll back up real quick so you can see them. Okay, now the question is, what is the relationship between the number of sides and the sum of the interior degrees? All right, I'll tell you. It turns out that the sum of the interior degrees is going to increase every time you add on a side. If you think about a triangle, it's got 180 degrees inside of it. A quadrilateral's got 360 degrees inside of it. It looks like it's increasing by 180 every time. So we're going to take the sum of the interior angles. We're going to be trying to look for that, which will be derived by this. We're going to take 180 and multiply it by the number of sides. But we can't exactly do that, because if we did 180 times 3, for example, that would be the number of sides for a triangle, but we get 540. That's no good. So we have to figure out a way to adjust this a little bit. Think for a moment about how we could adjust this number of sides. All right, answer coming in. We're going to take the number of sides, which we're going to abbreviate with n, and we're going to subtract 2 from that. Don't believe me? That means 180 times n minus 2. In other words, if the number of sides is 3, I'm going to take that number and subtract 2 from it. 3 minus 2 is 1. 1 times 180, you guessed it, 180. If I want to do it for a 4-sided shape, a quadrilateral, 4 in here means 4 minus 2, which is 2. 2 times 180, 360. I wanted to tell you that this sum of interior angles of any polygon is always going to work because I said so, and also because it's a mathematical rule. Speaking of mathematical rules, let's take a look at the next page where we talk about this mathematical rule, or these two mathematical rules. The sum of interior angles of a polygon is going to be 180 times n minus 2. We just talked about that. And each interior angle of a regular polygon is going to be that same exact expression divided by n, because as we talked about on the previous page on that chart, for example, if we're taking a look at a triangle is going to have 180 degrees inside of it total. In order to find each interior angle, we're going to divide it by n, the number of angles. So, for example, if I'm looking at the square, we're taking 360 and dividing it by 4. We're taking, for a pentagon, we're taking 540 and dividing it by 5. So that's the procedure there. All right, now you're going to take a look at the next activity. Pause the video and see if you can do these check for understanding questions, and then come back to see if you got them right. All right, for the first check for understanding question, it asks the sum and degrees of the measures of an interior angles of a nonagon with 9 sides. So all I'm going to do is take this same formula, the formula for the sum of interior angles of a polygon, and substitute 9 in for n, because it's got 9 sides. 9 minus 2 is 7. 7 times 180 is 1260 degrees. We're supposed to also determine the measure of each interior angle of a regular octagon. You know, octagon's got 8 sides, so we're substituting n into the formula here and here. That's 8 for here and 8 for here. 180 times this gives you 6. 180 times 6, and then divided by 8 gives you 135 degrees. And that was on the chart, actually, so we didn't necessarily have to guess at that, but this is an easy way to show you how to find that out. Let's move on to the turn and talk. There are diagrams on your document. Take a look at the diagrams and try to determine the sum of degrees of exterior angles of polygons. Now we're not talking about interior angles like we were talking about back here. We're talking about exterior angles. An exterior angle might look like this. If I extend one of these lines out here, I know the interior angle here is 60. So what's the exterior angle? Same thing here. What's the exterior angle? Think about that, pause the video, and then see if you got it right. Here we go. In these two pictures, we have 60, 60, and 60. We have 90, 90, 90, 90. We know that already. But the question is, what do the exterior angles measure? Well, I know that if this angle is 60, the exterior angle is going to be a supplementary angle to that angle. In other words, this 60 and this angle are going to add up to 180. So each of the interior angles, we can tell, measures 60 degrees. So all three exterior angles, well, let's see. I know that this exterior angle is 120. That's 60 plus 120 is equal to 180. So if this is 120, and this is 120, and this is 120, that's going to be 120 times 3. Of course, that's equal to 360. For this next one, we have these 90s, and each of the interior angles is going to measure 90 degrees. That means that angles A, B, C, and D, these exterior angles, they're also going to measure 90 degrees, because 90 plus 90 is 180. So all four exterior angles add up to, well, let's see, 90, 80, 270. Hey, what do you know? That's another 360. There's a pattern forming here, folks, and it's not a coincidence. All three exterior angles, all four exterior angles, when you're looking at a polygon, the exterior angles of a polygon should always equal up to 360 degrees. Now that you have that piece of information that in any polygon, the exterior angles should add up to 360 degrees, try the check for understanding, see if you could do this, pause the video, and then come back to see if you got it right. All right, it asks for which polygon does the sum of the measures of its interior angles. You know this formula already. We had it on the top of this page. And then we're supposed to have that equal to the sum of the measures of its exterior angles. Well, you know that we just talked about is going to be 360. So 180 times n minus 2 is equal to 360. All we got to do is solve that problem, solve that equation. We get n equals 4. N equals 4 gives me that it's a square. And here's the diagram that proves it. In this square, all of the interior angles sum up to 360. All of the exterior angles are the same thing. They also sum up to 360. All right, that was the first lesson in Unit 9, the Polygons unit. This was about intro to polygons. Hopefully we hit this target. We derived the formulas for interior and exterior angles of regular polygons, and then we applied them to specific shapes. Your task right now is to take a look at the problem set from this lesson to try to answer these questions. If you are all done with that problem set, you can check your answers on another YouTube video that I've recorded. It says Unit 9, Lesson 1 on it, so it should not be too difficult to find. All right, students, good luck studying.